All right, so welcome back, and here's another LeetCode problem. So today we're going to do a similar one to what we just did previously. Basically what this is it's called minimum sum of mountain triplets 2 here. We just previously did the minimum sum of mountain triplets 1, and so it's kind of like the prerequisite for this question, but you don't really have to do it beforehand. All that's really different here is that basically the constraints are much more intense. So basically the topmost or the maximum length of this array can actually be 10 to the power of 5, while previously I think it was just up to 50. Similar thing here where the numbers range to a much larger range here, so you're just given a much broader constraint. So what you would actually need to write out here is we previously did like O of n squared, but that wouldn't be optimal, or I guess it wouldn't be performant enough to handle this input size, so we want to do something more of the size of O of n here. All right, so how do we do this? Well, I'm assuming you already kind of know this question, but we'll quickly go over it. Essentially here, what you have is you want to iterate through these numbers from left to right, and you're looking for mountains. And so one example of this is 153 here, so you can kind of see the number rises from a smaller number up to 5 and then kind of falls down to the number 3 here. And so this is at indexes, let's see here, index 2, index 3, and index 4. And so the constraints that you have for defining a mountain is, well, the middle number has to be greater than the number on the left-hand side, but also the middle number has to be greater than the number on the right-hand side. And so basically you don't want a mountain that keeps increasing. You want one that increases and then kind of falls from that point on. And so what we have here is another thing where, okay, we also want to make sure that the ordering is correct. So the number on the left here has to be on the left and so forth. And so one catch here is that I showed you an example here where they're all consecutive, but they don't have to be. And so let's find another example where they're not. And so let's pick out the number 4, 7, and 2 here. And so you can kind of skip over numbers to construct this mountain. So this looks something like this. So 4 up to 7, and then I guess really it goes down to 2. So more like that. All right, so 4, 7, and then 2 here. And that's acceptable. They don't have to be all consecutive. So how do we do this? Well, the way we previously did it is we just kind of wrote an n-squared algorithm where we're iterating from left to right. And so we're just going to iterate between this range. And so we're always going to be looking and pointing at the middle value. And so because the middle has to be in the middle, you can't be on the leftmost integer or the rightmost. You don't look at those ones. You just iterate between this range here. And so you're just going to say, okay, we look at this number and we say, okay, what's the minimum on the left-hand side and what's the minimum on the right-hand side? So then you get 8, and then you get 1, and then you see, okay, is this a valid mountain? Well, it's not, because 8 is greater than 6, and 6 has to be greater than the number on the left-hand side. So that's not valid. And we basically just keep iterating here from left to right, and so we could find one at this point here when we're at 5. So what's the minimum on the left? That's 1. Minimum on the right, that's 3. And the middle number is 5 here. And so that is a proper mountain in that case. All right, so the issue here is that we're doing a lot of repeated work with calculating over and over again what's the minimum on the left, what's the minimum on the right, and just a common algorithm and kind of data structure that you work with for finding like the minimum is something kind of like prefix sum, but we're gonna kind of do like prefix and suffix where we're not taking the sum on the left-hand side as we go, but we're actually maintaining the minimum. So what this is going to look like is we're going to have two arrays here, one called prefix, one called suffix, and they're going to be an array that looks like this. So like so, and this is a very common technique that you use for a lot of problems, even easy level problems, so I highly recommend knowing this. So we're going to basically maintain from left to right what is the minimum number up to that point. So initially the minimum is going to be 8, right? Because when you're iterating from left to right, 8 is the minimum most number. But then we see 6, and that's our new minimum. All right, so at that point, from indexes 0 to 1, the minimum number is 6. And we see 1, and well, that's another new minimum. But from this point on, we see that 5, well, that's bigger than our current minimum, so we maintain 1, and then so forth. 3, well, 1's still the minimum. What suffix is basically the exact same thing, but in reverse. So we look at 2 first, that's the current minimum. Then we look at 10, well, we want to keep 2. Then we're looking at 7, we keep 2. Then we look at, say, 8 here. And I guess I'm showing you a different array. So let's kind of keep looking at this array. We're doing from right to left once again. So 3, and then we keep 3 instead of 5. Now we want 1, and then basically we keep doing 1 here. All right, so it's basically the exact same thing, but in reverse. All right, so this is basically going to allow us, the prefix is for what's the minimum on the left-hand side, and suffix is for what's the minimum on the right-hand side at any point there. All right, so let's go ahead and implement this. So first thing that we're going to want to do is essentially say, okay, if the length of our numbers is less than 3, well, we need at least 3 points here, so we just immediately return a -1 in this case. Otherwise, well, we want to be keeping track of like a minimum sum here. And so typically the pattern here is you just want to set to the maximum number possible. And so one edge case here is you return -1 if there is no mountain or triplet that you found that's valid. And so to get around that, you just say, okay, if the minimum sum is still infinity here, then that means we never found a proper mountain. So we just want to return -1. Otherwise we did, and so we wanted to return that result. All right, and so before we kind of iterate between kind of the range here to find these mountains, we first will want to create our prefix and kind of postfix sum here. And so let's go ahead and implement that. So, but here is when we actually find the triplets, but prior to that, we want to find the prefix and also find the suffix. And these are the data structures I just previously showed you here. All right, so how do we do this? Well, essentially, what we have is, let's go ahead and define this prefix array, which initially, let's just set it all to infinity. And we know that it needs to match the size of our nums array. So we're just going to kind of do the exact same thing here for suffix, so just like so. But the difference here is one's going to be iterating from left to right, the other is going to iterate from right to left. And so we can just say, okay, for the I, or let's think here, for every number in our nums array, we're just going to keep track of what's the minimum num so far. And so let's just initially set that to infinity. And so we're just going to say, okay, well, and we want to iterate from left to right here. So let's just do enumerate nums because we just need the index here. So we say, okay, the prefix at I is going to be equal to, let's think here, nums. So we want it to be the minimum. So with each iteration, we're also calculating potentially the new minimum. And it's going to be the minimum of whatever the current minimum is, and potentially a new one, which is our current number here. All right, so I hope that makes sense. We're just iterating from left to right. We're keeping track of what's the new minimum that we might have found. And then with each iteration, we're just maintaining at each index what is the current running minimum number. All right, so we're going to do exact same kind of similar thing here, but sort of in reverse. So for suffix, it's going to be like so, but we're going to want to iterate through these numbers backwards here like so. And so with that, in order to also be populating the array backwards, we're just going to say, okay, at index, length of num minus I, and then -1 here. All right, so I think that makes sense. Oh, and we just want to be populating the suffix data structure. And so from this point on, we then want to actually find these triplets. So with each iteration, we can quickly look up an O of 1 time because of these data structures. Otherwise, it would take O of n time. And so we can just say, okay, what's the minimum on the left-hand side? Well, that's going to be prefix at I. Then what's the minimum on the right-hand side? Well, that's going to be, or we want I minus 1 because we don't want to include the current number, right? Because if we're looking at what is the middle number with each iteration, which is I, then we don't want to include that number, so we do I minus 1, and on the right is I plus 1. So how do we know if it's a valid triplet or mount in this case? And so we just say, okay, if what's on the left is less than what's in the middle, and what's on the right is less than what's in the middle, then we found a valid mountain. So triplet is valid. And so in that case, we want to potentially update a new minimum sum if we might have potentially found a new minimum. And so we just do it like so, and this is just common code and a pattern where you just take the minimum, whatever is the current running minimum, and this new sum here. So minimum on the left plus the current number plus what's on the right hand side. So let's go ahead and run this. Oh, what's wrong here? So invalid syntax for I in the range. Here, so what's this saying? By non-built-in math.inf times the length of, length of nums. I must have accidentally deleted that. So looks like we're just shy of the answer here. So we're returning clearly invalid results. And so what is that? So basically we have minimum, we want to start the maximum. Minimum on the left, minimum on the right. Makes sense. And so from this point on, I want to make sure that our current number is greater than those results here. And we say min left, and that makes sense. What are our prefix and suffix arrays? And so we iterate through them like so. Minimum number. Not sure why that's min sum. That makes sense. Each iteration we have this. That makes sense. Let me just check my notes here. So, -1. Oh, it's because we're using prefix twice here. We want to use suffix, like so. And success. So sorry about that. Essentially, naturally with our suffix data structure, that's keeping track of from left to right what is the current kind of minimum. And so whenever we want to see what is on the right hand side of this middle number in our triplet, and so what is that current minimum? Well, it's going to be in our suffix data structure. I hope that didn't confuse you too much, but I hope I explained myself here. So once again, this runs in basically O of n time and space complexity. That's because we're using these suffix arrays to basically allow us to go from O of n squared down to O of n by allowing us to quickly look up in O of 1 time what is kind of the current running minimum on both the left hand and right hand side at any point in our array. All right, so I hope this helped a little bit, and good luck with the rest of your algorithms. All right, thanks for watching.